Bismillahirrahmanirrahim. So here is a problem that we have. Random variables Q and G have the joint PMF given below. The joint PMF is given here. And we are to find out whether Q and G are independent, and part B whether Q and G are correlated. So let's begin with part A first. Independence of Q and G, right? So the two random variables Q and G are independent if and only if their joint PMF, represented by this, is equal to the product of their marginal PMFs. So marginal PMF of G multiplied by the marginal PMF of random variable Q. If this equality is true for the random variables Q and G, only then we can say that random variables Q and G are independent. So to test for this equality, we have this joint PMF here, but we need to find out the marginal PMF of the random variable Q and G. So the marginal PMF of random variable Q, for example, is given by, we will sum all the values of probability values corresponding to random variable G for a given value of random variable Q, right? So G. What it means is, for a given value of random variable Q, for example Q is equal to 0, we will sum all the values of the probabilities corresponding to random variable G here, right? So in other words, we will sum these values of the probabilities in this row here. So 0.06 plus 0.18 is 0.24, plus 0.24, that is 0.48, and plus 0.12 is 0.60 here. And similarly for Q is equal to 1, we have 0.04 plus 0.12, that is 0.16, plus 0.16, that is 0.32, and plus 0.08, that is 0.40 here. So what we have here is marginal PMF of random variable Q here, right? Likewise, we can find the marginal PMF of random variable G, and now we sum the probabilities values corresponding to random variable Q now. So for a given value of random variable G, for example, G is equal to 0, we sum all the values of these probabilities corresponding to random variable Q, all the values of random variable Q. So this is 0.10. In other words, we will now sum the columns here to find the PMF of random variable G. So this is 0.30, and this is 0.40, right? And this is 0.20. So we have the PMF of random variable G now with us. So we have the PMFs of both the random variables. Let's write them down here. So PQ of Q, it is 0.60 when Q is equal to 0, right? And it is the probability 0.40 when Q is equal to 1, and this is 0 otherwise, right? Similarly, for random variable G, we have a 0.10 corresponding to G is equal to 0. We have 0.30 corresponding to G is equal to 1, 0.40 corresponding to G is equal to 2, and 0.20 when G is equal to 3, and this is 0 otherwise. So we have now the marginal PMF of random variable G also with us. What we need to do now is test for this equality here, and for this we need to construct the product of these two probability mass functions. So we build a table similar to the one here, but the table will contain the products of these probabilities of these two random variables. So let's begin constructing that table. So this is the product of the probabilities, not the joint PMF, right? So the table is similar to the one we already have, but the values are obtained by multiplying the values of the probabilities of the probability mass functions. This is not the joint PMF, keep this in mind please. So Q is equal to 0 here, and we have Q is equal to 1 here, right? So for Q is equal to 0, we have this probability 0.60. For G is equal to 0, we have this probability of 0.10 from the probability mass functions. So what we are going to do now is multiply these probability pairs. So 0.60 multiplied by 0.10, this comes out to be 0.06. So in this way, we are going to evaluate all the entries, all 8 entries in this table, and then compare them with the ones here. Even if a single value is different from the ones we have here, this equality will not hold. And we can say then that the random variables K1, G, and are not independent. However, if all the values in this table come out to be the same, that we have here, then we can say that this equality holds and the random variables Q and G are independent. So let's find out. The first value is the same at least. So let's continue. For Q is equal to 0, we have 0.60, and for G is equal to 1, we have 0.30. So 0.6 multiplied by 0.3 is 0.18. So Q is equal to 0 and G is equal to 2, we have 0.24. And Q is equal to 0.60 and G is equal to 3, we have 0.20. So this is 0.12, right? Likewise, for Q is equal to 1 now, we have 0.40, and corresponding to G is equal to, we have 0.10, this is 0.04, and Q is equal to 1, 0.40 multiplied by G is equal to 1, 0.30, this is 0.12. For Q is equal to 1 and G is equal to 2, we have these probability pairs 0.40 and 0.40, this is 0.16, and for Q is equal to 1 and G is equal to 3, we have this probability pair 0.4 multiplied by 0.20, this is 0.08. So if we look at this table and compare it with this one, so all the values here, all 8 values here are the same that we have here. So in other words, we can say now that this equality holds. So is equal to the joint probability mass function is basically the product of the marginal probability mass functions. So this equality holds for the given pair of random variables Q and G, and therefore random variables Q and G are independent. So we can say Q and G are independent. Right? So the first part we are done with. Now with the second part, which is the correlation of Q and G. So one thing that we must remember, when two random variables x and y are independent, then they are always uncorrelated. When x and y are independent, then they are always uncorrelated. But the converse is not true. But the converse may not be true. In other words, if we find out the random variables x and y are uncorrelated, so it is not necessary that they are independent also. So in other words, the uncorrelation of random variables x and y is a necessary condition, but it's not sufficient for the independence of random variables x and y. So in this case, we have found out that Q and G are independent. So it must be that they are uncorrelated also. So the test of correlation is done by evaluating the covariance of random variables x and y. So the covariance of, in this case we have random variables Q and G, the random variables Q and G, the covariance is given by this function, the expectation of Q minus mu Q and G minus mu G, right? And this function is the covariance is also presented like this. This function, it can be shown to be equal to this one, expectation of QG minus the product of the expected value of Q and the expected value of G, right? So and this expectation QG, the expectation of QG is called the correlation of QG also. So covariance Q comma G is QG minus the expected value of Q and the expected value of G, the product of expected value of Q and G. So we need to now find out these three quantities, right? So let's begin by finding the expected value of Q. So the expected value of random variable Q, which is also presented by mu Q, is given by this summation. So we will sum all the products, actually we will multiply the value of the random variable with the corresponding probability and then sum this together. So expected value of Q, we'll multiply this value with this probability, we multiply this value with this probability and then sum them together, right? So this is 0 multiplied by 0.6 plus 1 multiplied by 0.4. So this is obviously, this is 0 and this is 0.4, this is 0.4 here. So expected value of Q is 0.40. Likewise, the expected value of random variable G is given by this summation now. The value of the random variable G multiplied by the corresponding probability, right? So expected value of G is given by, so this is 0 multiplied by 0.1 plus 1 multiplied by 0.3 plus 2 multiplied by 0.4 plus 3 multiplied by 0.2, right? So expected value of G is, this is 0 plus 0.3 plus 0.8 plus 0.6 here. So this is 3 plus 8 plus 6, this is 1.76 plus 0.6 plus 0.8 is 1.4 and plus 0.3 is 1.7. So expected value of G is 1.7. So this is the mean value of random variable G, or the expected value of random variable G. So the third quantity, the expected value of QG is given by this double summation. So Q element of SQ and G element of SG will multiplied by Q multiplied by G, and this is multiplied by the corresponding value of the probability of the pair, right? So expected value of QG is given by, so Q is equal to 0 multiplied by G0 multiplied by 0.06, so this is 0, right? So Q 0 multiplied by 1 multiplied by 0.18, so this is again 0 because of this Q is equal to 0 here. So and then 0 multiplied by 2 multiplied by 0.24, 0, 0, and this entire row sums out to be 0 plus this value also because G is equal to 0 here. So the product for all these values, these 5 values is 0 here, and plus this is 1, Q is 1, G is 1, and this is multiplied by 0.12 here, right? Then we have Q is equal to 1 and G is equal to 2, right? And the corresponding value is 0.16 here. Then Q is equal to 1 and G is equal to 3. We have 0.08 here. So all these values are summed together. This is 0.12 plus 0.32 plus 0.24, right? Expected value of QG comes out to be 4 to 6 to 8, right? 2 to 5 is 6. This is 0.68. So expected value of QG, this is also called correlation of QG. So correlation of QG is 0.68, and this is non-zero, which means that random variables Q and G are not orthogonal. Q and G are not orthogonal, right? Had it been 0, we could have said that Q and G are orthogonal, right? But these are not orthogonal now. So let's now find out the covariance from this formula we have here. So covariance of QG is given by 0.68, we put 0.68 here, minus the product of the expected value of Q and G. The expected value of Q is 0.4, and this is multiplied by the product value of G. This is 1.7, right? So we find out 1.7 multiplied by 0.4 is basically 0.68. So covariance of QG is 0, right? So as we expected, the random variables Q and G are uncorrelated. So Q, G are uncorrelated because we have already found out the random variables Q and G are independent. So when they are independent, they are always uncorrelated. And as I have said earlier, the converse may not be true always.